All right. Can you hear me? Yeah. It's 3 o'clock, so I'm going to start with this talk. So this is a talk or a presentation about high availability solutions for MySQL. My name is Max. I'm working at SkySQL. I used to work for a place called MySQL AB before they got acquired by various companies. That's when I left, by the way. And basically at SkySQL we sell services around MySQL, so support, training, and consulting. So we're still doing the same thing we did before, just different company. And yeah, so the topic today is high availability solutions. So I'm gonna have a small introduction about just high availability in general, and then I'll go into different solutions. So at my company we're fairly agnostic. We do whatever the customer wants, pretty much. So that's why we have a wide variety of solutions. So we're not kind of restricted by partners or companies or whatever. So there'll be stuff from Oracle, and there'll be stuff from other companies as well here in this presentation. And of course, if you have questions at any time, feel free to interrupt me. There's half an hour after this between the talks, so I can go over by a lot. So the first thing here is, what is high availability? So that's the thing everyone wants, right? But when you ask what actually do they want, they don't always know what they want. So I was looking for a definition, and this is what I found on the internet. It's a system design protocol and asset, blah, blah, blah. Basically, the idea is ensure a certain degree of operational continuity during a given measurement period. So the point is that despite things breaking, we still have some kind of service available. That's what people normally want. So high availability might have a specific, there's actually a measurable unit for high availability, which is percentage. How much time is your system available of the total time? But normally what you want is to have some kind of operational continuity despite things breaking. So you don't want your customers to see a 404 web page when your system is down. You want them to see something else. If you look at the actual definition of availability, it's of course how big a part of the time your system is available. So you often talk about nines, how many nines your system is available, and it means how many percentage of the total time your system is available. So 1 9 would be 90%, 2 nines, and so forth. And the good thing with this is, well, the good thing for marketing departments is that there's no scientific method of proving that a system is a specific level of nines. So you will often see people marketing stuff at, oh, this is 5 nines, this is 6 nines, and then when you ask them, so how did you get to this number, they'll be extremely vague because, you know, there's no actual science behind it. It's just, well, we decided that this was available, so we said 5 nines. And normally it's the marketing team that decides, not the actual engineering team either. So I know this because we did the same thing at MySQL AB when I was working there. So I mean, all of these things you have to kind of, you know, they don't mean a whole lot when you see someone mark. I listened to a talk when a guy was talking. I'm not going to say which product, but he said they have 9 nines. He said 10 nines availability. So someone asked, are you sure? He said, yes, it's 10 nines. And I calculated it was like a microsecond per year or something. It doesn't seem plausible, but that's what they were saying. So you will see a lot of this stuff, and basically, you know, all of this doesn't mean a thing. It's every system is different anyway. So whatever something is marketed as doesn't mean that your system will have that. And they can always say, well, you know, you happen to be at the time when it failed, and if you had run for 1,000,000 years, on average it would be 5 nines. So they can't be wrong either because it's statistics. So there you go. But this is the actual definition of availability, and what high is, of course, depends on your demand. So for some people 90 is high, and for some people 10 nines is not high enough. Now there's a lot of ways there's a lot of ways of creating a highly available system, but there's also a lot of problems, potential problems associated with it, and there's a lot of terminology that's kind of when in the HA, I don't know, space. So a few things that I will mention in this talk is synchronous versus asynchronous. And of course, this doesn't really mean anything either, because no thing is ever really synchronous, right? An old colleague from MySQL used to say to all his customers, everything can be made synchronous by adding weights. So everything is, if you look down if you go on a low enough detail, everything is asynchronous. So it's just a question of where do you actually look and what do you do. So we will see that some of these systems have synchronous replication, meaning that from a client perspective, when a client gets a validation, the operation has been committed on two different systems, even though the actual process is not synchronous. It goes first on one, then on the second. But because we add a wait, we wait until it's gone all the way to the second system before we tell the client it went through. We make it seem synchronous. So, I mean, that's the thing. A lot of customers say, okay, we need it to be synchronous. They will say, okay, that's fine, but, you know, what the price you pay is wait time. And they're like, oh, well, we don't want to pay that price. Well, then you don't want synchronous replication. So there's always a price to pay. Shared disk, well, shared disk is, does anyone know what shared disk is? A few. Well, shared disk is something that used to be used especially in big enterprises, right? And no one uses it anymore, pretty much. Well, it's not true. We have a lot of customers who use it, but if you have a SAN or something like that, that's basically shared disk. But a lot of solutions, well, especially in MySQL space, are now based on shared nothing, meaning that you run system and they all have their own boxes, and you don't share anything. It's all through messaging that you take care of the HA aspect. So you don't have to buy a big SAN or anything else that's expensive. So it's kind of a different way of ensuring the availability. Like all NoSQL technology is kind of based on the shared nothing architecture, where you just spread out stuff and there's some kind of duplication, so that if one machine goes down, the data is stored somewhere else, so it doesn't matter. And a single point of failure is a very important term in HA. That's of course what you want to avoid at all costs. You want to make sure that there's no such point in your architecture which would take down the whole system. If this fails, the whole system will fail, and that's what you want to avoid at all costs. So if you have a good system, you don't have a single point of failure. And then the failover versus switchover. Failover actually means automatic failover. Well, no. Failover means that it's automatic, so no one should ever say automatic failover. I say it all the time, but it actually is already implicitly in failover. It means automatic. And switchover means that it's a manual process. And when we look through some of these solutions have a failover built into them, so it's automatic. You don't have to do anything, and others don't. This doesn't mean that you have to sit there and plug something in if something fails. It just means that you have to add something to it to make it automatic. So a good example would be MySQL replication, which is kind of an HA solution, maybe. But something that's used a lot for HA. Of course, if the master fails, well, the master fails, and all your clients trying to talk to the master, they won't get an answer because the master is not there. So you have to add something to make it a failover. So you have to make sure that there's some kind of layer that redirects your customers to the slave when the master is gone. And there's a lot of utilities out there for that, so it's not like it's complicated, but it's not there out of the box. And then the last thing, split brain, node fencing, Sonnet, and quorum are about, well, that's basically it. No, so they're dealing with when you have high availability, an HA architecture, especially in a shared nothing environment, meaning that you don't have a central anything, it's just boxes. You have a potential problem in that everything is done by communication between the boxes, right? What if the communication breaks down between the machines? So let's say, just a simple thing, you have two machines, right? And they're exact copies of each other, and they're running. And every time you write to one machine, the other machine is updated, and vice versa. Everything is great. Then the communication between the machine goes down. Now if you write to machine A, the write won't go to machine B. If you write to B, the write won't go to A. And if you write to both at the same time, they will no longer be synchronized, right? And kind of game over because your data is no longer consistent. And that's what you want to avoid at all costs, because then, of course, you kill your system. And there are different ways of avoiding this, and I mean, it's called a split brain scenario to have these two machines that are no longer in sync. And there are different ways of avoiding this, and these here are a few. So node fencing just means fencing off a node that's no longer responding. I mean, the main problem with this is that it's difficult to tell whether a machine is actually down or it's a communication problem, right? So you can't communicate to the machine, did it crash or is it still there? So the easiest solution is to just assume that it's dead. But because you're not sure that it's dead, just make it dead, then it's dead, then you know, right? You don't know what you don't know, but if you kill the machine, then it will be dead. So that's why you have something called stun it. Who knows what it means? Excellent. Shoot the other node in the head, right? So, okay, I can't talk to him. I don't know if he's dead or not, so let's make sure he's dead. And then we can assume he's dead and continue, right? So you just make sure that guy is dead. So that's actually something that's very used, because you need that. Otherwise you cannot you cannot allow the other machine to be up and running and take requests, because then it's no longer in sync. Yeah, go ahead. Right, so the question was what happens when the machine comes back up. So that depends a lot on what you're using and how, but the main idea is to make sure that even if it comes back up, it doesn't automatically start until it's synchronized. So then it depends on what you have underneath, what's actually your HA architecture. A very simple method is to make sure it never comes up. So you have to manually start it to come up, then you can ensure that it's synchronized. And you might say, well, that's not good, it's not HA, but it is, because you make sure that if one machine dies, it's still running. Then some DBA has to come in and get it up, but you don't care because you already passed the main crisis, which was the guy dying. So that's the easiest way, is just to make sure you have to manually start it. But there can be others, and it depends a lot on what you're using behind as an HA solution. Quorum is another way of dealing with this. This is one of the solutions we're going to look at. They use quorum. Quorum just means that there's kind of a voting, and as long as you have 50%, over 50% you're good. If you have less, you kind of commit suicide. And some solutions use that, and some use a more complex version of that. Right, so any questions about these? So that's kind of terminology, and all of this stuff will link to what we're going to talk about later. So split brain was the thing you want to avoid. So the two machines having different data. So if they're both up, even though they can't communicate. So split brain should have a big no in front of it. Right. So this is kind of the things you need to think about when you design a high availability system, like how much availability do you really need? Because normally it's easy to get more, but you actually have to pay for it. So if you start by saying, okay, I require synchronous and 5 nines, and then you get the price tag, and then you say, okay, maybe I don't require that. So, you know, you have to think about what do you really require? I mean, everyone would like to have a synchronous system with 10 nines availability. Just, you know, it would cost a lot of money. You need 9 data centers and, you know, whatever. So it's normally a price you have to pay. And when it comes to synchronousness, like the second bullet here, do I require no loss of data? Normally the price is in response time. So if you want something to be synchronous, your response time, or I mean your average response time for a query will go down. Will go up. The response time will go up. The throughput will pretty much remain the same, but each individual query will be a bit slower. So if you're running some kind of website where it's important to get responses quickly, this might not be a solution. And of course, if you have geographically distributed HA solution, normally just the latency between your different data centers or whatnot is just too long, so you don't want to have a synchronous solution. It will take too long. And each time taking this time means that your client is waiting, which means he might go somewhere else while he's waiting for an answer. And then, of course, if you want automatic failover, number one thing is to test it. We have a lot of customers who actually put this in place, and then they had a crash and it didn't work. and then they you know have a lot of issues. They call us, well, it doesn't work. It's like, so, well, did it work when you tested it? They were like, well, we didn't actually test it. So it's like, okay, what do you expect? And another thing is, in some cases, you want to have automatic failover. In some cases, you don't. Automatic failover is great, but you can also have false positives and things like that, which makes the system switch over, even though it actually wasn't. The other node actually hadn't crashed. It was just unresponsive for some other reason. So it's kind of a price you pay, and especially bigger companies where you can afford to have DBAs on call all the time. You might actually prefer manual switchover, because you just wake up some poor DBA and say, okay, go and look at the system. If you're a small shop, of course, you don't have that many DBAs, and you know it might cost. You prefer to have it automatic, so it kind of depends on your system. And then number one thing, and then the last thing, of course, is to test what if this component fails, what happens to the system, what if this came out. I'm going to talk a bit about the new things in 5.6. And well, MariaDB 10.0, they have replication enhancements that they are not out, but I'm still going to talk about them because they're pretty cool. And then Tungsten, Galera, and some shared disk solutions, cluster, and so forth. So who here has already used MySQL replication? Okay, about half. Has anyone used 5.6? One person. All right, excellent. Sorry, what? 5.6? I have no comment. Right. So most of you know this. Half of you have used it. So MySQL replication. It's the good thing with MySQL replication is it's there. You don't have to do anything. You download MySQL. You have replication built in. All you have to do is turn it on. MySQL replication is based on the binary log of the master. So when you have a master server, you turn on the binary log, and every data changing operation will be stored in this binary log, right? And that's the thing you see here. It looks like, I don't know what it looks like, some kind of battery for like a scale or something. So that's the binary log. So every time there's a statement written to on anywhere in the MySQL server, it goes into the binary log at the same time. Now, if you really care about HA, you don't use MyISAM, you use InnoDB. Who uses MyISAM here? One guy there admits. Okay. So the problem with MyISAM is, of course, that MyISAM, I'm not talking about the problem with MyISAM. The problem with MyISAM is it's not consistent even on one server. So don't even think about trying to have it consistent over two servers. So MyISAM, your server crashes, it might be in an inconsistent state, right? There's no crash recovery, there's no rollback, nothing. So it's impossible to guarantee any kind of synchronization across two servers, because you don't know what's going to happen after your server comes back up if it crashes. So if you really want HA, you can scrap MyISAM. InnoDB is good because it has crash recovery. So if a transaction is committed, then it will be applied even if there's a crash. If a transaction is almost, you wrote commit but you didn't press enter, it won't be there. So it's only if the transaction has been committed. So it's already consistent on one machine. And what you have to do if you care about HA is you have to make sure that the binary log and the InnoDB is synchronized. There's an option for that, which I can't remember right now. Binary log something. So you have to make sure that when you commit something in InnoDB, the binary log will get the operation at the same time. I mean, again, nothing is really synchronous. So it's actually done in 3 steps. They do prepare on one, and then they commit on the other, and then they validate on the binary log again. But it ensures that if there's a crash, the binary log and InnoDB will be consistent. Again, because the slaves will be reading the binary log, so you don't want something in the binary log but not in InnoDB, because then your slave will have the operation but not your master, and so forth. So there's a complex mechanism for making sure that the binary log and InnoDB are synchronized. And this allows our slaves to sit there and read the binary log of the master, and the slaves, by reading the binary log, they will get everything that ever changes on the master and nothing else. Because the binary log is synchronized with InnoDB, it will always be the same. So we'll have all operations. And the binary log actually has two modes. It's got 3, but One is stupid, so we're not going to talk about it. But it has got two modes. It's got statement-based and row-based. And statement-based means that we actually store statements in the binary log. So if I do update in my binary log, well, it's binary, so you can't read it. But if you read it through a translator, it will say update. The exact statement will be in there. And this is great, except for the fact that statements can be non-deterministic in many cases, which means that if you then apply the same statement on your slave, it won't give the same result, and they won't be synchronized. So game over again. So this is why it's better to use row-based, where instead of storing the statement, we store row images. So you have an image of the row before the operation and after, well, depending on the statement. If it's delete, there's no after. If it's an insert, there's no before, and so. But we store images of the rows. We say, okay, these are the rows, how they were, and this is how the rows should look. And so we don't have to care about whether the statement is deterministic or not, because we don't store the statement. Right. And the slaves, they have two threads. There's an IO thread and an SQL thread, and one of the threads is connected to the master. It just sits there and reads the binary log, ships it over, and then there's a local thread that applies the stuff on the slave. So it's basically a three-way process, which is here. So you commit, and you write to the bin log on the master. Your client will receive an OK here. Then your slave will ship the changes to itself, write it in a relay log, and then there's another step when the slave will actually apply what's in the relay log. So it's extremely non-synchronous, right? Because as soon as we press commit, the client gets the commit, and then we start shipping stuff to the slave. So that's one thing to note here. It's completely asynchronous. There's some other features of replication. So it's a master-slave relationship, which kind of means that, well, one thing it means is that the master just doesn't care about its slave. So when you configure MySQL replication, you configure the slave. You don't really configure the master. The master just is. And you configure a slave and say, you want to be a slave, you should start replicating this guy from this bin log position and so forth, and he does it. One of the problems with this was that replication is based on the binary log positions of the master. So if you look here, a slave keeps track of where, it wasn't me, where in this log is the slave. So in case the slave would, I don't know, crash or stop for a while, it just continues reading the binary log from where it left off. Yeah, it's kind of a sequence. The problem with the sequence is that it's kind of lost. So if you have a slave that's a master to another slave, you lose the original sequence of the master, because the slave will have its own binary log with its own sequencing number, and it won't be the same. And this is something that was fixed in 5.6. In 5.6 you have something called global transaction ID, which kind of follows through. So the original writer of the query will kind of give each transaction a stamp, and that stamp will go through the whole way. So it's easy to reconfigure slaves and attach new slaves and change the master and things like that, because you have a fixed sequence that doesn't depend on which machine actually applied the query. It just depends on which machine the query came from in the beginning of time. Well, so it's easy to set it up, and it's all good. The problem becomes when you have, let's say you have two slaves like this, and then the master fails, and you want this guy to become the new master. The problem is that you mapping where he was to his binary log, there's no mapping. And you can do it. You have to go through the relay log and read them and compare the different sequence numbers, but it's not anyone would, say and would do. So it was difficult. You needed some kind of automated process. There are some tools for doing this, but with 5.6 you don't need to care about this because it's easier. Yeah, go ahead. Yeah, it's just the fact that the binary log position is based on the server that applied the statement, and it's only saved from what kind of one level, and then it's gone. Now, I mean, there is a tool that can do it. So if you're using MySQL 5.5 replication, and you're having these issues, there's a tool. Actually, it's coming up in a slide. It's called MHA. It was developed by former MySQL AB consultant. So it's a tool that does it. It basically reads through the relay logs of all of these and maps these transactions to the original number, and then resynchronizes the slave. So there's a tool that does it. No, it's open source. It's on Google, code.google.com. MHA, master. It's coming on the slide. Master high availability, I think. I mean, I should know we support it, but I can't remember. Yeah.
Yes. Is there provision in this for, say, the master goes down and the slave takes over, and then the master comes back? Is there a way to reverse it and update it?
Well, it's the same problem with the keeping track of the transaction, the binary log. I mean, normally what you would do is you don't care who's master and the slave. They should be fairly identical. So when you have promoted one of the slaves to the master, and then if you reuse the old master machine, it would just be a slave. Yeah, you don't want to care, because it's. I mean, every time you do a switchover, it's some downtime. Even it might be fairly short. There's still some downtime, so you don't want to do it for no good reason. Yeah, so that's a good question. So the MySQL replication has no conflict resolution. That's the thing to remember. This means that I mean, it is a master slave, so you can set up slaves, and actually a master can be a slave of its own slave. So you can have two-way replication between two machines. The problem is that there's no conflict resolution. This means that if you would have a conflict, it's not detected. Well, it's not fixed, but it's not even detected. So you will actually have two machines that are not synchronized, and you won't even notice. So, I mean, again, if you have a good reason for doing this, I mean, what you have to do is make sure in the application logic that you cannot have a conflict. I mean, there are fairly easy use cases where there can never be a conflict. For example, I mean, we have a customer who's a gaming company, and they had different data centers, and the user would, when they log into the game, they would automatically be directed to the nearest data center. And here you can easily have replication between the different data centers, because a user can only be logged in from one location at one time, so there cannot be any conflict. You cannot log in Europe and North America at the same time, because it's not allowed. So the application makes sure that there is no conflict, and in this case you can do this. But note that there's also no multi-source, so one slave can only have one master. So if you do multiple data centers or something, it has to be a circle. It can't be directly across. Right. So what is replication used for? So originally it was designed to be used for load balancing, for websites where you have a lot of reads and a lot fewer writes. So the idea is that you can read. Your clients can read from the slaves, and the few writes you have will go to the master and then propagate to the slaves, but all your reads will go directly to the slaves. So this way you can scale your website. And that's what it was designed for, and it works fairly well. The problem is, of course, that you don't have any guarantee that, because it's not synchronous, you don't have any guarantee that if you do a write, that the write is already on the slave when you read it. So there is no guarantee, and that's kind of the price you pay. Then, of course, it's used a lot for HA, so you can have a standby master. So you have a master, you have a slave. If the master fails, the slave becomes the new master, and people can run it. And while the customers are using the slave, then you can start examining, okay, what went wrong and whatever. But basically, it's just a standby. And same if you're doing some kind of upgrades, of course, you can do a control switchover. You switch to the slave. As the slave becomes your master, you do the upgrade on the master, you switch back, and then you do the upgrade. Well, you start by doing the upgrade on the slave, then you switch to the slave, and then you do the upgrade on the old master, and then you leave it until the next time you have to do an upgrade. So it allows you to have a minimal downtime for upgrades and things like that. And I mean, also maintenance stuff. If you do some kind of optimized table that will block your table for a really long time, you do it on the slave first, and then when it's done, you switch all your clients to the slave, and then you do it on the master or something like that. And then, of course, it's used a lot for geographical replication, because Because when you have long geographical distances, you don't want to have synchronous. You want to have something that's not synchronous, like replication. So we'll see a few synchronous solutions, and these can often be combined together with the standard replication to create a global replication. Then in MySQL 5.5, they added something called semi-sync replication. Has anyone ever used this? Yeah, I haven't heard of anyone who has ever used this either. I mean, the idea is good, but yeah, well, yeah. So it's actually not there as it's shipped with MySQL, but it's a plugin, so you actually have to load the plugin, but then you can start. But it's there, so you have to write 2 statements, and then it's there. So what semi-sync replication does is that it ensures that if you commit a transaction, it will be shipped to at least one of the slaves before the client receives the validation of the transaction. So it's semi-sync because it's only shipped to the slave, it's not actually applied on the slave. And it's only one, so we don't guarantee that every slave, or I mean, the server doesn't guarantee that every slave has it, but it guarantees that one slave will have the transaction. So it can be used, but it's, I mean, to me the biggest problem with this is that I haven't heard of anyone who has actually used it, so I don't know if it actually performs well or not. We did some testing and it wasn't as performant as standard replication, which is normal because you have the wait time. But very few customers actually use it, so I don't know. But it's there, so you can test it if you think that standard replication is not fast enough. I mean, doesn't guarantee enough. By using this, you can guarantee at least that your transaction will be on one slave. But it's still not synchronous. Any questions about this? Okay. So it's not half written. So if you go back to the replication, this is the standard case, right? We have 3 phases: commit and write, ship, and apply. So basically, in the semi-sync, basically the steps 1 and 2 are in one. So basically, you write your transaction, you press commit. Now this master waits until one slave says I have it, and then it says OK to the client. Yeah, to the client. So now this means that if your master would fail just after, we know that okay, at least one slave has it, so we know that the transaction is somewhere. If you don't use semi-sync, then if a master crashes, you cannot guarantee that the last transaction actually propagated somewhere. Yeah. No, so what you have to do if you use this is you have to check which slave is the most advanced slave. Again, MHA does this automatically if you use MHA, but it's fairly easy to do, but you know, you would have a script to do it with, like MHA or something. But every slave stores this information, so it's easy to check which slave it is.
Let me ask this follow-up to that. Does it sometimes pick this slave, sometimes pick that slave, or?
So the master doesn't pick its slaves who
Right, they're both reading the
yeah. It's just the first slave that says I have it, okay. It doesn't care which slave. Well, it doesn't. No, you have to look at each slave. If the master fails, you have to check. Okay, where are you? Where are you? Where are you? And then you say, okay, you're the furthest. You're the new master.
But they could be inconsistent. One of the slaves may have this transaction, the other one may have this transaction.
Yeah, but they're sequential. So, if with the one that's the furthest ahead, will have all up to. You don't skip transactions. If the slave dies, does the master hang? No, the master doesn't care about the slaves. So the master will go on even if all the slaves die. Or you mean if you do a semi-sync? Yeah. So semi-sync actually has a timeout, so it waits until a specific timeout. Yeah, that's not possible. Yeah, in order. Well, you should go ahead and try it and tell me. I mean yeah, pretty much. I mean, this adds another layer of security, yes, but it's still not synchronous. Go ahead.
Technically, if somebody does an incorrect commit and it wipes the data, that replicates over.
Yes. Yes. So, I mean, most HA solutions are built again, it's hardware failure, not user failure or software failure. Yeah, that's but I mean, yeah, you can use delay. There's this thing in 5.6 called delayed replications. You can make sure that they're a certain amount of time behind, kind of, but it doesn't really solve the problem. But it's a way of getting around it. I mean, if you have people who delete your databases and stuff, I think you have bigger problems to worry about than HA architecture. Well, it's the same. You know. Right, I already talked about MHA. So this is the MHA thing that automates this. It works with standard replication, also with semi-sync, but it doesn't work past 5.5 anymore. So it doesn't work with 5.6 because they changed the way the replication works in 5.6. But we have a lot of customers who use this because it's so easy. You have replication already. You just add this. You don't have to change anything. You just add this, and it does automatic failover. And it's automatic slave promotion. That's one of the main things. If you have master multiple slaves, it will look at each slave and say, okay, this guy is the one that should be the new master. So it's great. It's basically a bunch of Perl scripts, actually. It's not, I mean, it looks nice, master high availability manager, but it's actually just Perl scripts. And there's one program that's running, which just monitors the master. And if it fails, it just launches scripts on slaves to do all this stuff. Right. So that's cool. So then we come to 5.6. So I kind of already said, the number one thing they added in 5.6 is this global transaction ID, which the stamp that follows with each transaction all the way. So it makes it really easy to reconfigure masters and things like that because when you compare two slaves, you will see, I mean, the slave doesn't store its own binary log position, but it stores the global transaction ID with each transaction. So you can compare two and you can get the missing ones easily and stuff like that. So you basically just tell a slave, okay, this is your master, resync yourself, or resync thyself, and it will. So that's pretty cool. Another thing they added is multi-threaded slaves. So one of the problems with MySQL replication is that it's single-threaded on the slave, which, I mean, MySQL replication was added in like 2001, if I remember correctly. You know, and no one had more than one core. I mean, kind of, which made it, I mean, almost. But now you have like machine by default has like 12 cores or something. So quickly, if you're using up your hardware well on your master, the problem is your slave cannot because the slave process is single-threaded. So if you're on the master, you're constantly using multiple cores. Your slave will be lag behind your master all the time because it can't use all its cores. And 5.6 has a kind of not really a proper solution, but kind of a semi-solution. You can add a thread per schema. So if in your MySQL database you have multiple schemas, you can have one applier thread per schema. So this only helps if you have multiple schemas and if your workload is well distributed between them. If you have one schema where all the work takes place, this doesn't help at all. So it's kind of this assumes that your schemas are independent, that you can reorder your transactions are not, the order of your transactions are not dependent, there's no dependency between the schemas. So within each schema, the transactions have to be in the order, but between schemas, it doesn't matter which order transactions come. So it kind of means that each transaction has to touch only one schema. If your transactions touch multiple schemas, you cannot use this. Yeah.
What happens if for some reason the master gets disconnected from all the slaves because they never get to switch those down? Does it continue running on its own and we resync if they come back?
So that now it depends on what you're using. If you're using some kind of Stoneit mechanism, what you do is you kill the master, you make sure it doesn't come back up, and you make someone else the master, and then you're good. Yeah, so normally you have some external monitoring, right? And this monitoring won't be able to connect to the master either. So it will say, okay, let's assume the master is dead, and if it's not, let's kill it so that it really is dead, and then it makes someone else the new master. So that's kind of the default thing to do. But that's again when I said you can have false positives and stuff. So that's why you normally want to have some kind of delay, not kill the master immediately. Okay, 2 seconds and let's kill it. No, the slaves they don't care. You have to have some external program that does it. So I mean, a common program for this would be Pacemaker, or Pacemaker with CoreSync, which is a fairly common combination to use with MySQL replication, or MHA, which does this as well, or MHA combined with Pacemaker. Right. So that was 5.6. So I mean, 5.6 is fairly cool. Which client? Oh, well, so you need to have some front end that does that. So with replication, there is nothing there. You have to do it yourself. So you need a VIP or something, and you need to switch you switch the VIP. Yeah. So with replication, you have to do it yourself. Some of these solutions will actually have it built in, but replication has nothing built in. You have to do it yourself. But I mean, any VIP will kind of work. A virtual IP address. So you just switch where it points to, and then the client automatically goes to the new master. So for HA, it's fairly new. I mean, they changed a lot, and it's fairly new. So I would recommend testing it. Well, I mean, to be fair, we had customers who needed some of these features who started using it already in October when it wasn't even a release candidate. So, I mean, the next thing I'm going to talk about is MariaDB 10.0. It's in alpha, and we have customers who use it already. So it's it really is kind of based on your need and what risk you're prepared to take, kind of. But again, I mean, for example, if you have a project that is supposed to go live in like 6 months from now, then definitely use 5.6, or at least try it. If you have something that's already running, production system, you have like hundreds of thousands of dollars per like a day or a minute or something, I wouldn't switch to 5.6 immediately. So it depends. Then you shouldn't use this because it will be in. Yes, by default it's off, so it's something you can turn on. But by default it's off. Oh, it typically, I mean, the idea is for stuff like someone mentioned. What if your user says delete all, and then you still have the stuff there? Yeah, it can be hours. I mean, it can be used for other things. Testing. I mean, honestly, it's not the most useful feature. That's why it's lowest here. But I mean, some kind of testing or that kind of thing. Yeah, kind of a backup. Yeah, you can have a 3-month delay. Yeah, you can have anything. Magic. 2 seconds is very short. Just kind of pointless. I mean, it depends on why would you use it? Why would you use it? The question is, why do you use it? So then, why would you use it? And then the number comes from that. If you use it because you want to see how your data was a day ago, well, then you make it 24 hours. If you use it because someone might delete your tables, then maybe 1 hour is enough. Yeah, exactly. If you some companies it takes microseconds, and you have one customer we have, they have a counter on how much money they're losing because the system is down. So as soon as someone screws up, the counter starts going up, and so it's like everyone has a number. And I mean, it's part of the environment where the way they work, and no one will get that taken out of their salary. It's just to show how important time is for them.
So the time delay, for example, you have play as the recording server.
For example, yes. I mean, your time delay is just automating this, but you can also do it yourself. You can just stop the slave, and you don't have to use this feature. You can, I mean, even before 5.6, you just stop the slave, then it's already time delayed in a way. So. All right, so MariaDB 10.0. So who knows what MariaDB is? Okay, not even half. So it's kind of it's a branch of MySQL. It's kind of some of the original developers of MySQL, including the founder, they quit when Oracle acquired them, and they created their own company, and they're kind of developing MariaDB. But it's basically a branch, so it's kind of based on the same thing. 98% of the code is the same. So they have added some features and things like that. But But they're now, so they have something called MariaDB 5.5, which is based on MySQL 5.5, which is fairly similar, but it has a few more features. Basically, that's the only difference. But now they're doing something called MariaDB 10.0, which is kind of a bit further away. They're adding a bit more features. So the reason why I'm talking about this is that they have a really cool feature called multi-source replication. So this is completely alpha, and as I said, we already have one customer using it, even though it's alpha, because multi-source is such a cool feature. And they're also adding something. They're also adding global transaction ID, but it will be a different implementation than MySQL because they. So MySQL, the global transaction ID is per server. So the server that writes your transaction stamps the transaction, and that server ID will follow the transaction forever. In MariaDB, they do it differently. They have something called domains, which is configurable. So a domain can be one server and it can be many servers. So basically, each transaction gets a stamp per domain. And the reason for this is well, it's partly because it should work with multi-source, and partly because it gives you great flexibility. So basically, okay, well, let's go look at what this can do. So first of all, what you can do with multi-source is you can have a fan-in slave, right? So you can have, let's say you're some kind of store, your Target or whatever. You have lots of retail shops all over the country, and every store will have the data for what they sell. And then you have somewhere centrally located, you have the central data warehousing where you get all the information. And basically, with multi-source, all you have to do is set it up, set up replication like this, and it will automatically store all the information. So, multi-source assumes that each source, that there are no conflicts between. Again, there's no conflict detection, so you cannot have conflict between your sources. A bit in the same way as with the parallel slave. Right, and you can also then do something like this, like a star schema thing. But you can do, I mean, if you use multi-source, you can have any kind of configuration pretty much. If you set it up to do it. So with multi-source, pretty much you can have 5 servers, and every server replicates to every server, kind of, if you want. The problem is the fact that you have to remember that each source, I mean, you have to make sure that there are no conflicts between each source in the application logic. And I mean, that's the assumption. If you have conflicts, then it will break. So the assumption, you have to do it in the application logic. And what they do here is that each source kind of corresponds to the domain. I said the global transaction ID is a domain. So it basically means that instead of having a server here, you can actually have a replication hierarchy here, and then you replicate. You have like 3 servers that replicate each other, and then they replicate somewhere else as well. So, and these three servers will be in the same domain because they will have the same data. This means that if one of these fail, you can just replace it with another one. But the transaction sequencing will continue from where it left off. So the transaction sequencing is not per machine, but per domain. So it can be multiple machines. What? Well, it doesn't have to be circular anymore because you can do multi-source. So you don't need in standard replication you have to do circular because you don't have multi-source. Here you don't have to use circular because every machine can replicate from many machines. If you have three machines or 3 data centers, you can have each data center replicating straight to each other. With standard MySQL, you have to do it in a circle. So with standard MySQL, if you have, let's say, West Coast, East Coast, Europe, you have to do a circle. So West Coast goes to East Coast, goes to Europe, goes to West Coast. If East Coast goes down, the circle is broken, you have to reconfigure across. Yeah, exactly. The only thing is, again, every machine in the same domain, I mean, the different domains have to be non-conflicting. Right. So I mean, it doesn't exist yet. I mean, it exists as alpha code, but it's not a GA product. But I just took it up because it's a cool feature. Like a what? Well, so I mean, in each domain, you have to the domains have to be, as I said, non-conflict. I mean, separate domains cannot have conflicts. So if you have an auto increment, you cannot use the same auto increment in a different domain. It won't work. So that's kind of the idea. Everyone in the same domain. I mean, it's basically you can't use the same primary keys in here and there. It won't work. Yeah.
What was the motivation for multi-site replication? Was it more for high availability?
No.
Or was it more for reducing the bottleneck of central database increase?
I mean, it's not high availability at all. This kind of makes it less available because it becomes more complex. But the reason for this is basically because of requests. People have been asking for this feature a long time, right?
So real quick question on the auto number question.
Mm.
So essentially the master would have its own parent-child relationship and that would be maintained, but the IDs would not necessarily line up between all the places. Is that kind of what it does?
Yeah, I mean,
You're not going to guarantee the same ID everywhere, but you're going to guarantee that like a sales order header would have line items and items.
yeah, I mean, if you use auto increment, you would have to make sure that each domain, you have this auto increment. Make sure that each domain uses separate auto. So it's like, if you have 3 domains, the first domain will get 1, 4, 7, 10, and so forth. So they don't have a step on each other. So, I mean, yeah, offset. It's already there. It's already. I mean, the variables are already there, but right. Well, and this is another picture. It's the same thing basically. You have like domain A, domain B, and then they both go to server 3, and then server 3 can have others that replicate, and they can replicate both domains, and they can be in different order. That's the whole point. So each domain becomes kind of a parallel thread also on this master because they're guaranteed to be separate. I don't want to spend more time on this. The guy who's developing this has really good blog posts about about this feature, so I can show you his blog post. You can read about this if you're interested afterwards. No. I mean, I don't know. It won't be the same, that's for sure. But they might implement the same thing in a different way, but it won't be the same, for sure. Well, MySQL is still being developed, so by Oracle. I mean, LibreOffice kind of there's only LibreOffice, right? Oracle still supports it? Okay, well then it's the same. And LibreOffice still gets, I mean, so Oracle produces MySQL, MariaDB takes whatever Oracle produces and adds their own stuff to it. That's pretty much it. It's more complicated than that, but that's the really basic story is that. Right. Okay, but this was the MySQL replication. I've spent way too much time on this already. So then we have some other solutions. There's one called Tungsten Enterprise, which is by a company called Continuent. And they've kind of implemented their own replication, so it's also not synchronous, it's asynchronous. But they don't use the standard replication, they have their own replication library. It's written in Java, it's called a replicator. It also uses the binary log, so it's fairly similar to the MySQL replication. I mean, the basics, it's similar, it uses the binary log, but they use their own library. And what they've done is that they've bundled it together with a manager or a monitor and a client-side connector, which means that your client, so basically when there's a master failure, they will switch here and automatically switch to your client as well. So you don't have to add this VIP layer or anything, it's automatically done for you. No, it's called Tungsten Enterprise, and the company is called Continuent who does it. It's a third-party company. And I'm so far behind, so I'm going to go. So this is what you can do. It's cool. It's written in Java. It's partly open source. So it's kind of a replicator, a manager, and then the connector. And the replicator is open source, and the other parts are not. So you have to pay for the other parts if you want the full solution. But the replicator itself is open source. Because it has the for each client, it has a connector. So every database connection will go through its layer, and that's why it's splitting it. And this connector is aware of the configuration here. So when there's a change, it will also change the connector. So that's how it does it. So it's kind of like a proxy in between your client and the MySQL server.
That client library does not replace something like a using MySQL library or act like a SQL server?
My answer is yes. I've done training on it. I can't remember actually how exactly it's done. But it's something like that. I can't remember which one exactly. If I remember correctly, it's more like a proxy. So you connect to it, and then it looks like you're connecting to a local local connection, but then it's actually you're not connecting to a local MySQL, but you're connecting to this connector. But I've tested a lot of different. I'm not sure this is correct, but something like that. Then there's another solution called Galera. Has anyone heard of Galera? Forehand. Has anyone heard of Percona? No, not Percona. Percona. No. Percona XRDB cluster. That's what okay, it's the same thing. No, basically, so Galera, it's a company called Codership, and they developed this replication library, which is replication. Kind of, it has hooks inside InnoDB. So it doesn't use binary log or anything like that, but it hooks on the storage engine level, which then you replicate. And this Galera library is open source, so in theory anyone could use it for free. So in order to use Galera, you have to use a binary where you have this Galera library built in. So you have to either compile MySQL yourself, or you get it from Percona XRDB cluster, or MariaDB has something called MariaDB Galera cluster, and these are the same thing. One is Percona server with this built in, the other one is MariaDB with this built in. Codership also builds MySQL, so the community edition of MySQL with this, so you can also get that if you go to Codership's website. So it's kind of 3 versions of it, but you cannot use the normal community edition because you have to have this built in. Which for many customers that's scary because you can't use the community edition, but it has fairly good features. So they call it virtually synchronous. So it's almost synchronous application, but not quite. And we'll see exactly how the commit goes in a moment. But it's not really synchronous, but it's much closer than the standard application. There's no slave lag. Because every transaction, when it's committed on every server. So you can have large clusters, and I've actually heard of customers who've had large clusters and they don't have a huge problem with latency. In theory, you could have a huge problem with latency because every time you commit a transaction, it has to be committed to every single server in your cluster. So it could be fairly slow, but most people who have tested this have been fairly happy with it. But I would not, for example, use this across huge geographical regions because there's latency. Okay, so that's a good question. So this pretty much allows you to have multi-master because you can commit transactions to all of the saves at the same time. And in normal InnoDB, inside InnoDB you have locks, right? So if one transaction changes one row, that row is locked, so another transaction cannot change the row. Of course, you don't have logs across the different machines because they're only validated upon commit. So this means that if you use this in a multi-master fashion, you can have locking problems at commit time. So in InnoDB, if you have a lock, the next transaction will hang and wait for the lock to be freed. Here, the transaction will go on, and then you press commit, but then another of the machines, actually someone changed the same row, so it will actually fail a transaction at commit. The transaction will fail. If you have a conflict, one of the transactions will fail in this case. So this kind of, if you have an environment where you would have a lot of potential conflict, you shouldn't use it with multi-master, but you can actually use it with just one master. You don't have to have multi-master. You can just, like with replication, you put all your writes on one machine, and then you have no conflict. But every sleep can, if the master will fail, you just switch to another master, and it's already up to date and it's running and everything. So it's good. Yeah, you would again need to have some kind of layer, VIP or whatever. It's not built in, no. Because it actually supports multi-master. So in this case, you could actually write to every machine, and it supports it. It's just that you might have a lot of aborted transaction because of lock conflicts. But it actually supports it. It's not like my standard application where no one will notice if you have a conflict. Here, if you have a conflict, the transaction will be aborted. So also, they use quorum as the kind of the split brain guarantee is a quorum. So this means that you cannot have only 2 servers, because then you will never have a majority. So you need to have at least 3 machines for this to work. So if one machine fails, the others, well, they will continue because they have 66%. So let's see what happens. So if you have here you have 3 servers in a Galera in a Galera setup. So you write to one of the servers. You do read or write. So the first thing that happens is that you just process the transaction normally, locally. You don't talk to any of the other servers. Then when you press commit, the transaction is validated by all the machines. So basically this transaction is sent out to all the machines. The other servers validate that there is no conflict on their end. Right? So if at the same time you touch the same rows on another machine, this will be aborted, this transaction at this stage. Once the other servers have validated it, we send the OK back to the client and we're good. Yeah, you have to just write code that's transaction failure aware, which you should normally write anyway, because transactions could fail for other reasons as well. So if you write bad code, you might have a problem with this. No. No, but I mean, the problem is that you might have a lot of these abortions, which is annoying, right? Because
I was coming from PP4 to legacy systems 2 bit.
yes, it depends on how if you had some kind of placeholders for aborted transactions before, then yes. If you don't, then not really. But I mean, yeah, because here it might fail on commit, but it could have happened if you just have one server. It could also fail at any point, right? There might be a connection problem. There might be anything. So.
Why would you have, in this scenario, why would you have
What do you mean 2 rows? Oh, because you could. It could be. Let's say you have a. Let's say you have a store. Yeah, you have a store and 2 people are buying the same product at the same time. I mean, it could be anything. It really could be anything. And one happened to be in this server, the other one at that server. So it could be a bank account. Well, I mean, I wouldn't use it for a bank, but the important thing to note here is though. So here the other servers, they validate the transaction. Then we say OK to the client, and then the other servers apply the transaction. So there's actually not fully synchronous replication. That's why they call it virtually synchronous, because to make it a bit faster, the client gets OK before it's been applied on the slaves. I mean, the slaves have this change, so they will get it, but you might not see it right away. So there's a small lag in between there. And the reason for this is to make the transaction time, faster, to not have so long latency between each commit. Well, they acknowledge that there's no conflict. They acknowledge receiving it and that there's no conflict, and that's it. Yeah, exactly. But I mean, the commit will happen really soon after, but it's not. It's not a guarantee. It's not synchronous. Yeah. So that's a cool thing. If anyone's interested, go to a Codership or Percona XDB cluster or MariaDB Galera cluster and try it out. It's fairly cool. But remember, you need at least 3 servers, otherwise it will be less available than one machine, right? If you have 2 machines, it's funny, but a lot of people think that 2 machines is a good scenario. So let's say you have 2 machines, and you use, for example, this. If one machine fails, the other one will say, "Oh, I have less than half," so it will commit suicide. So this means that your system will become like 50% less available than one machine is, because any machine failure will cause both to fail. So that's why you need 3 to make this highly available. Right. I'm a bit behind time, so okay. So then we have the shared disk stuff. There's not much to say here. You have something like a SAN or something, and you have 2 machines that are kind of ready to use the SAN. In MySQL, you cannot have an active-active setup. It needs to be active-passive. So this machine can be running, but this can't. Well, so MySQL can be running, but you can have the machine running. Depending on the file system, you might even have the file system there as well, but you cannot have both MySQL servers running. So basically what you do is you have one MySQL server attached to the SAN. If this MySQL server crashes, this MySQL server starts up, it does a crash recovery, and then it's available. And of course this is completely synchronous because they use the same disk. So once you write here, it's written, and there's no problem with synchronization. And again, in order to make this work, you need to have a virtual IP or something in front that does the switch for the client. But basically all this to say that MySQL works with shared disks, right? But it's not an active solution, meaning that the big downside with this is that when the master fails, the server fails, the second server has to do a crash recovery. So there is a downtime. And I mean, how long the downtime is depends on certain variables like the redo log size. But even if you tune that down, it's several seconds, probably at least a minute of downtime before your server is done with its crash recovery. But this is fully synchronous solution. Right.
What is your preferred way of creating a network distribution system, maybe without managing the other SaaS like
So which two would communicate?
or
Oh, they don't communicate. The standby is not. It shouldn't be there. It cannot be running. You cannot have the other MySQL server running because they're going to use the same disk, and you need some kind of global locking. And MariaDB would. I mean, it doesn't exist. You cannot do it. The other one has to be shut down.
What if there's a mount point on both servers, both systems are up, second server doesn't have the actual MySQL service running?
Yeah. So that's the best you can do. You can, well, it depends on the file system, but if you can mount the file system so that someone else is writing to it, which you can with some file systems, then you can do up to that point, but you cannot start the MySQL server until the other one has died. So that's kind of
Like the pacemaker function.
yeah, exactly, and that's what the pacemaker corresponding would do. It will start up the other one, and you have some kind of stonage making sure that the first my guy doesn't come up anymore as well. Right. That's a shared disk. Then there's something called DRBD. Who knows what DRBD is? Oh, a lot of people. Exactly. Distributed replicated block device. So it's basically a poor man's SAN, right? So if you can't afford a SAN, you just you kind of you replicate your disk instead. So it's kind of like if you had a SAN, but you don't. Basically, for MySQL, it's exactly the same as if you had a SAN. I mean, from what you do and stuff. You can only have one running. You can have it mounted only if. So basically, what happens is you have a replication between two machines. Basically, below the file system, you have this DRBD that replicates your disk or your file system changes to the other server. And so it doesn't. It's not only MySQL, but it works with MySQL. But the same problem is you can have it mounted on the other machine, but MySQL server cannot be running. So you have the same issue with having to wait before, and you also need an external VIP and so forth to do the switch. So it's really similar to shared disk. So this is kind of a same category as shared disk. It's just cheaper because you use commodity hardware for it. And we have a lot of customers use it. I mean, it's cheaper, but there's also a price, of course. It's cheaper, so why would anyone have a SAN? Well, the price is, of course, that you use a network communication between the servers. So it will be slower. The actual replication will be slower than if you use a SAN, right? Because he replicates something across the network and changes. Right. Any questions about the shared disk stuff or DRBD? Then the cool thing is that you can combine this with replication. Why would you do that? Well, because your shared disk or DRBD is your master, and then you have slaves that replicate from this master. So now if your master fails, you don't have to take one of the slaves to become the new master because you have your shared disk. You just run up the passive master, it becomes the new master. So you still have the downtime during which you don't have a master, but all your slaves are running all the time. So you can read stuff all the time, but you have a small the downtime where you can't write stuff. So that's something that's actually very used with our customers. They have some kind of SAN or shared disk solution for the masters, and then they have lots of slaves. especially web customers who have mostly reads and fewer writes. Well, I mean, it's just shared disk, but you have, I mean, you have something here where you have a shared disk, and then the slaves replicate from this master. And if the master fails, the other machine will just come up and use the disk of the old master. Exactly. So it could be anything. It's just in case this, someone takes a chainsaw on this machine, where you run up the other machine and you're still good because you have the disk. You don't have the. It looks like the master came back up, even though it's a different machine, because the files are the same. Okay, there's one more solution, and it's called MySQL Cluster. Who has used MySQL Cluster? Oh, quite a few guys. It's perhaps the worst named product in MySQL history. So, everyone I've ever talked to thinks MySQL Cluster is a cluster of MySQL servers. It's not. It's something completely different. I mean, it's you know NoSQL, right? Who knows what NoSQL is? Oh, not that many. Well, so this is like a NoSQL solution, but with a MySQL front end. That's what it is. Don't laugh. That's really what it is. Basically, what it should have been called. Well, its actual name is NDB Network Database, and that's a better description than MySQL Cluster. I'm going to skip this stuff, but basically, in MySQL you have something called a storage engine, which is InnoDB or whatever, which is where you store your data. In MySQL Cluster, instead of using InnoDB, you kind of use a clustered storage. So basically, your storage is not local; it's these data nodes where your data is shared between the data nodes. So every table you create in MySQL Cluster will be partitioned into different bits, and each partition will have a master and a slave. So depending on the number of data nodes, you will have a different amount of partitions. So if you have, for example, here we have 4 data nodes. This means that each table would have 4 partitions, and each data node would be a master of one of the partitions, and then there would be a slave as well. So it's kind of, you split up your table. You split up your table on different machines. It's kind of like most NoSQL solutions do, right? The idea is to be able to scale your writes. Yeah, well, it's a bit like RAID technology as well. And you do it through a MySQL frontend. So it's good because it actually scales writes. None of the other solutions scales writes. So all the other solutions where you write something, it has to be written in every of the nodes. Galera, it has to be written in every node. Replication has to be written to every slave. Here, because your table is actually partitioned, you only write to 2 always. It's automatically, you don't see anything. Okay, don't get too excited. It has a lot of drawbacks, right? So I mean, I love Cluster. It's one of my favorite products. But the problem is that because you don't use InnoDB anymore, it's a different storage engine. It has a lot of drawbacks, which are mainly due to the fact that it's distributed. So for example, doing joins and things like that is very hard because the data is not in one machine. You have to load data from multiple machines, then join together the results. So MySQL traditionally only uses a nested loop join algorithm, which means it's kind of like nested for loops to do joins. So you go into the first table, take the first row, then you go to the next table, take the first row, then the third table, take the first row, and so forth. Then you join these, and then you go back. With Cluster, this means that every time you do this, you have a network hop. So joins used to be extremely badly performant. Now there's a different algorithm. There's a batch key access, so you can take more. You can take more rows at once. So you have less network hops, and you can also. There are algorithms for linking results. So you can have, if you have. Anyway, so now it's a bit better, but it's still nothing. For anything that you would use NoSQL, this will also be good. So it's good for key lookups and things like that, but for complex queries, it's going to be worse than InnoDB and anything else. Yeah, so if you look at this is actually how it's, so the partitioning scheme, basically every table is partitioned as many partitions as you have nodes. So if you add nodes, you also always have to add nodes in groups, so 2 at a time. So if you add 2 more nodes, this table will be repartitioned into 6 partitions. Each partition will have a master and a slave. And if you lose this guy, you still have the blue partition there, so you're good. But if you also lose node 5, then you've lost 2 of the partitions and you're kind of stopped. So you can always lose 1 node, but you can never lose. I mean, you might be able to lose 2 nodes as long as it's not the other one in the same group. So it is the solution with the highest availability. Remember in the beginning I was talking about the 9s and stuff. So this is the thing that was marketed as 5 9s. And I mean, again, there was no scientific data, but there was a reason for it. It works really well for specific scenarios. It was originally developed to run in telcos, so telecommunication environments like HLRs and stuff like that, where you put a box in a corner somewhere. It does primary key lookups all day long, and no one touches it, and it's perfect for this kind of stuff. But for really dynamic things and joins and whatever ad hoc queries, Cluster won't be your solution. Or I mean, it might be, but it's going to be slower than the others. So I'm not going to. I mean, it's very complex, this Cluster stuff. This is the basics, and I could tell you more, but I'm already way past my time. And Cluster has its own algorithm for making sure that there's no split brain. And well, you can ask me for the slides, not to mention it. So where does Cluster fit? If you have high demands on availability, then yes. If you need write scalability, it's the only solution with that. And again, with Cluster, you need at least three machines. And also, you need simple data models, simple queries, because complex stuff won't perform. I mean, it will perform them, but it will be slow. Right. And it's fairly complex to administer and manage as well, so that's a good point to remember. That's the difference with most NoSQL solutions are fairly easy. Any developer can set them up and start using them. Cluster, not so much. You need someone who actually knows what they're doing to set it up. So you actually need some kind of sysadmin to have Cluster. So that's a negative point with Cluster. All right. I'm going to skip this because I'm so far behind. So, in the end, I have this comparison chart with kind of the main criteria you could have for different 8-stage solutions and where all of these different solutions stand. So I only have one column for replication because they're all, even though they have lots of different features, the basics is the same. They're all asynchronous. They're all active-active. They all work with all storage engines and so forth. Right. And that's it. Any questions? It's not confidential, but I just finished them like an hour before, so no, they're not available yet. But well, you can send me an email at least, and I'll give them to you. That's for sure. But otherwise.